So today we're going to jump back to Algebra 1 a little bit and do some review and add on to that, if you will. We're going to talk about multiplying and dividing polynomial expressions. We'll start out real simple with a rational expression of 12 over 15. Now that's a fraction that can reduce, and the whole idea behind that is break this down into its factors, so we know that 12 is 3 and 4 and 15 is 3 and 5, and any like factors can be reduced because I have only multiplication and division, and I can reduce across multiplication and division. So any like factors can reduce because 1 over 1 or anything over itself is 1, thus it reduces to 4/5. That's the concept behind the entire day's lesson, except the algebra gets tougher. So in this case, we notice we have a whole slew of additions and subtractions. Now granted, 10 goes into 16, but since I have a subtraction in the problem and an addition in the problem, I don't have any separated factors. I can only reduce when I have multiplication and division of factors. So that word factors gives us a tip that we're going to need to factor this expression. So I have 5, which is my GCF, w minus 2 over w here, 2 and 8 with a positive 8 and a negative 2. Now notice I have subtractions, but they're within factors. There's multiplications between these two terms, multiplications between these two terms, and a division separating. So I have only factors and a division. So any like factors, anything over itself, can be reduced. So therefore I can reduce the w minus 2 and the w minus 2 and be left with 5 over w plus 8. Haven't done any multiplying and dividing yet. We're just reviewing principles of reducing factors. Again, this problem is going to be a little bit different. What I like to do is I like to make sure I have a positive x squared when I factor. Granted, I can factor this, but I like positive x squareds. So my first step in this problem would be to take and factor a negative out, get x squared minus 25. Pretty much like all my x's to be positive, if at all possible, all my leading coefficients, if you will, not just the x's, but my leading coefficients. And then I have an 8 I can pull out as a GCF, minus 5. Now this top, I have this negative on the outside. Those are perfect squares, so that's x plus 5 and x minus 5 over 8 times x minus 5. The x minus 5 are common factors, so I'm left with the opposite of x plus 5 over 8. So now we'll jump into our multiplication. There's a couple of different ways you can go about doing a problem like this. You can multiply across first and then reduce, or reduce and then multiply across. I base my opinion on whether or not the problem is going to get very large. So in this case, if I'm multiplying 12 and 49 together, that's going to get pretty large. So I'm going to take and reduce at least the numbers right off the bat. Variables don't scare me too much, so I'll just multiply those across when I'm done and then reduce. But with my numbers, I have 7 going into 49. So I would write a 1 here, cross the 7 out, 7 here, and then in this case I also notice that I have a 7 here and a 14 here. So I would get rid of the 7, put a 1, get rid of the 14, put a 2, and then I notice once again I have a 2 here and a 12 here, so I can reduce the 2 to a 1 and the 12 to a 6. So in the numerator, you remember when I'm multiplying fractions, I multiply the numerators by the numerators and the denominators by the denominators. I don't need a common denominator to multiply. In the numerator, I have no coefficients left other than 1. So I can say I have x squared, y, and z. In the denominator, I have a 6, x, y to the 4th, and z cubed. So now we're down to just our rules of reducing exponents. This is nothing but multiplication and division, and I take and find the highest degree and then subtract and keep my answer where the highest degree was. So I have x squared over x, which is x to the 1st in the numerator, y to the 4th and y, which is y to the 3rd in the denominator, y to the 3rd, or z, I'm sorry, z to the 3rd and z, which is z squared in the denominator, and I have that 6 left. So in this case, notice all the a squareds look just alike. You would think we can just reduce these top and bottom, but no go, because we have all the additions and subtractions. So I need to factor these so that I can reduce common factors top to bottom. Again, since it's a multiplication, I don't need a common denominator. On the top, I have a plus 3 and a plus 3. In the denominator, I have a minus 5 times a minus 5 multiplied by a minus 5 times a plus 4, and finally a plus 3 and a plus 4. Now I can reduce any common factor top to bottom or diagonally, but nothing straight side to side. So in this case, I notice I see a minus 5 and an a minus 5, an a plus 4, a plus 4, and an a plus 3, and an a plus 3. Thus, I'm left with a plus 3 over a minus 5. Here's another situation where I've got lots of polynomials, no real factors yet, so I'm going to have to factor each term. I see this bottom guy right here, and I notice my a squared is not leading, so I'm going to rewrite that to a squared minus 6a plus 9, just because it makes me feel a little bit better. And then I'm going to start factoring. I can do a 5-step or guess and check. This goes to a 2a and an a. I need to multiply to 9, get to 9, so that's 3, which is a 6 here, and then a 3, which is a 3 here. 6 and 3 when I'm foiling will get me my 9. It's all adding. I need a 3 here, a 1 here, and I've somehow got to multiply to 14, but when I'm doing my foiling I need a 19, and I have to have a positive and a negative, so I'm going to go 7 here, which gets me a 21 on this multiplication, and a 2 here, which gets me a 2, and 21 minus 2 is 19, so this is a positive and that's a negative. This is a plus 7 times a plus 7, and this term is a minus 3 times a minus 3. So now I have to look for like factors. See an a plus 7 and an a plus 7, and I think I'm done. I have no more like factors. So what's left is I have 2a plus 3, a plus 3, a plus 7. No need to multiply all this out. 3a minus 2, a minus 3, and a minus 3, and we can call it done. Now division, if we recall, is the same thing as multiplying by the reciprocal. So I'll just rewrite this first. And take the reciprocal. And start factoring away, because I have no common factors, just a bunch of addition and subtractions. This is perfect squares, so I have 6x plus 1, 6x minus 1. Even though this has a squared term in it, I know I have a GCF of 2x, giving me a 3x and a 2. In this numerator, I have a GCF of 10x, which leaves me an x and a 1. And then in this case, I have to either 5-step it or go ahead and do a little guess and check. I'm going to go with guess and checking. Go 3x, 2x. I need a 5, so I don't think that's actually going to work. Let's try this again. I'm going to go with a 6 and a 1. And then I need to get a -5, but I need a positive and a negative, so I'm going to go with a 1 here. That's going to get me a 6. I'll put a negative and a 1 here. That's going to get me a 1. Make that a positive, and -6 and positive 1 is -5, so that's going to work out. So now we find our common factors. Here's a 6x plus 1 and a 6x plus 1, an x minus 1, and an x minus 1. Now notice what I have left. Neither of these two are exactly alike, but the 2, the 10, the x, and the x are all multiples. So I can take and reduce those. I can reduce this 2 right here to a 1, this 10 to a 5, and this x reduces with this x. So what I have left is a 5 in my numerator and a 6x minus 1 over a 3x plus 2. Another division problem, rewrite it. A minus b squared over, I'll factor while I'm at it in this case. This is a 5a. I'm going to need another a to get a squared. Then I'm going to need 2 b's at the end. And I need to multiply to 2 but get 3 when I FOIL. Well, there's a 5ab, and if I go 2 more ab's right here, that will get me 3 if my second term is negative and my first term is positive. Then I'm going to multiply by the reciprocal. If I look at this term here, that is a difference of squares. I have my a's first and my b's second, so that's 5a minus 2b and 5a plus 2b over, and here's our buddy, the cubed, so we remember that's a minus b times a squared plus ab plus b squared. And now I look for my common factors. I have 2a minus b here, or 2 of these a minus b's, and I have 1, 2 down here, so I'm going to reduce all that. I have a 5a plus 2b and a 5a plus 2b, leaving me in the end with this 5a minus 2b over a squared plus ab plus b squared. So in this case, we have something known as a complex fraction, or a fraction over a fraction. Now, in this case, we notice there is one fraction over another fraction. I think it's easiest in this case to recognize this as a long division problem. So this is really x squared minus 1 over 3x plus 2 divided by x plus 1 over 3x squared minus x minus 2, which is what we've been doing all along. So I'm just going to multiply by the reciprocal. The top is a difference of squares. I'm going to multiply by the reciprocal, so notice this x plus 1 will go to the denominator, and this term will need to be factored. I'll use a guess and check. I need a 3x and an x, and I need to get a 2, but then a 1 after I FOIL. So I'm going to put my 1 here and my 2 here. Notice that if I need a negative, I better make this negative because that's a negative 3x, and this positive because that's a positive 2x. So now I look for my common factors, 1 here, here, and here. Notice what's left is 2 x minus 1 terms, so my answer will be x minus 1 squared. Alright, that's all we've got. Make sure you do your summary and you're connected.